Okay, let's continue our study of equilibrium. Let's say I have this particular reaction. I have hydrogen gas reacting with iodine gas to form, in a reversible manner, 2 moles of hydrogen iodide gas. What I'd like you to do is write the equilibrium constant for this process. So it's going to be Kc. We're going to use concentrations. So if this is the case, if this is my reaction, what's this equilibrium constant going to be equal to? Pause the video and try to write it. Okay, let me show you what the answer is here. We're going to take our reactants, which is just HI in this case, concentration of that, and we're going to raise it to its stoichiometric coefficient, which is 2. So HI to the second power. And then we're going to divide by the concentration of our reactants raised to their stoichiometric powers, which is just going to be H2 to the first power and I2 to the first power. And we're going to include everything because these are all gases. Remember, we only include gases and aqueous things in our equilibrium constants. And we're going to use this, and we should make sure that we understand that when we're writing equilibrium constants, that these values over here, these aren't the concentration of HI at any old time. It's a very specific time, and that is when it's at equilibrium. So when the reaction has come to rest. That's true for everything in the equilibrium constant expression. We only put the values of all species, their concentrations, once they have reached equilibrium. Now we're going to show you a way that we use equilibrium constants to solve some problems. So we've got our equation up top. We've got our equilibrium constant expression. And then often what we do to kind of keep track of what's happening to a reaction is we write what's called an ICE chart, I-C-E, where I stands for initial conditions, or initial concentrations. E, of course, stands for equilibrium. And C stands for any changes that occur as we move, of course, from the initial conditions through the change to equilibrium. So we'll do that for this reaction here. So I always like to write my reaction at the top of my ICE chart. So I just do this here, H2, I2, goes to 2HI, and then down the side here I'm going to write I for initial, so in this row are going to go the initial conditions, and then C, this is going to stand for the change that's going to occur, and then E, that's going to stand for our conditions at equilibrium. And let's just imagine that we're going to start with a system that has 0.0175 molar concentration of hydrogen gas and 0.0175 molar concentration of iodine gas and no hydrogen iodide. And we also know that what happens during the reaction is we happen to lose 0.0138 molar of hydrogen. With this information, we should be able to fill in all the remaining spaces in the chart, and we should also be able to calculate the numerical value of the equilibrium constant. Equilibrium constants always have a particular numerical value. So how can we do this? Well, I mean, you just look at the stoichiometry. We know how to do stoichiometry. We know that for every mole of hydrogen that reacts, 1 mole of iodine is going to react. So if I lose this many molar concentration of hydrogen, I got to lose that same molar concentration of iodine. Again, from the reaction stoichiometry, for every mole of this, of iodine that's lost, I'm going to gain 2 moles of this. So I'm going to gain twice this concentration. And if you do 2 times 0.0138, you get 0.0276 molar. You can do the math and check me on that. We're also going to recognize that if we lose reactant, in this case, we're going to gain product. Now we just take our initial condition, subtract or add the change to get our equilibrium value. So what's 0.0175 minus 0.0138? This minus this gives us 0.0037 molar for our equilibrium hydrogen concentration. And of course, we're going to get the same thing for iodine, right? It's the same numbers. So our equilibrium concentration of iodine is going to be the same for hydrogen and iodine, because you started with the same, and by stoichiometry, you lose the same. Over here, we started with 0. We gain 0.0276, and that means at equilibrium, we're going to have 0.0276 molar of our product. These are our equilibrium values, which we need, right? We need equilibrium values to calculate the numerical value of our equilibrium constant, so we can do it. So Kc, that's going to be my equilibrium concentration of Hi squared. So that's equilibrium volume of Hi on the numerator, 0.0276. We're going to square this. Let's not forget that. Then we're going to divide by the equilibrium concentration of hydrogen, which is 0.0037. We're also going to divide by the equilibrium concentration of I2, which is also 0.0037. And now we can run the numbers. 0.0276 times 0.0276. I squared the numerator. Divide by 0.0037. Divide by 0.0037. And that gives me 55.6 for the numerical value for this particular reaction.